thank you for the introduction. Right. Yeah, so we will continue in a Blackbox way, but not with verifying an existing controller, but here we want to, on the one hand, build a controller. So we want to synthesize it. And we'll also look at a setting where the sampling is really expensive. So we want to get this controller from a Blackbox system with only doing a few hundred samples on the Blackbox system instead of the 40,000 or what we just had in the keynote. So I'll first give you a short introduction on what is the actual problem we're trying to solve. Then I'll tell you about how we are going to tackle it and then how we evaluated it. So what is the setting for this? So we are actually considering a relative... Oh. Stumbling about it. So simpler setup without, so not a feedback controller, but like a feed-forward controller, or like we have a stateless function f, which represents our system, which has two types of inputs. On the one hand, we have some input, some observable thing about the environment. For example, in our larger case study, this would be the temperature. So we have some system that is very sensitive to temperature, and this should produce some correct output, for which we are here assuming that we can just quantify this with one real valued value, which we call R here, and we want a system that keeps this always positive. We can plug in a specification to actually get this, but in the more abstract sense, it's just we want to have this function always gives us positive output. And then we have this block C. So this is the controller that we actually want to build. And this takes our input, our environment observation, for example, the temperature, and it can produce some additional control input to our Blackbox function, like some trimming parameter to adjust for potential differences in temperature. So the system might behave different for different temperatures. And it also has one screw that you can turn to adjust it and to make it behave correctly for each of the different temperatures it might run. Okay, so know briefly what we want to do. So how are we going to do this? We're considering a Blackbox synthesis. So we don't have implementation or not a white box inspectable implementation of this function f, but instead we want to run simulations or executions on our function and then build a model that is targeted towards finding this control function. So it doesn't need to be an exact representation of everything that goes on in this function, but it should be good enough for us to build this control function and to verify that this is actually a correct control function according to some additional assumptions. So the high-level loop for this approach is depicted here. We're starting with some random samples and build a very small or very inaccurate initial model. And we try to find candidates on this model and then try to verify the candidates, which we can do even though we have an infinite state system with some assumption I'll get to in a moment. And either this very candidate is already correct, then we are done and we can hand this control function to the user. If this verification fails, or if we do not find any candidate because maybe the model looks like there is no possible control function for this model, then we also have an exploratory testing component that just runs some additional guided tests to figure out should the model look at different parts of the system that are currently underexplored, so we can open up new parts for potentially finding candidates there. So what is the model that we're going to use? So we're going to use Delaunay triangulations to build this, which are really nice because they can give us these linear interpolations. So here you see on the very left of the white box view of the system, which we don't actually have, but it's nice for illustrative purposes. So this is some simple examples. So we have the inputs on the x-axis and what our controller inputs on the y-axis. So the problem of now finding this continuous control function in this two-dimensional case means we want to have a path that goes from the very left to the very right and assigns one control input to every input of this function. Now, if we run a few samples and triangulate them, then we might end with a graph like in the middle. And additionally, if we know the function values, which are color-coded here, then we can also build from this triangulation this linear interpolation model, which tells us something, oh, here in this area, the function is probably negative, here it is positive, and the black lines are the boundaries in the model of what the model believes to be good states where we are allowed to pass through versus bad states which we have to avoid. And I also show here in red the original level curves from the white box view, so we have some indication how good the model is at the moment. But since this is all continuous, we can't verify anything with just finitely many samples if you don't add at least some additional assumptions to that. And for that, we're assuming that our function, like the function of both the inputs and the controllables, is Lipschitz continuous. And we are also assuming that we actually know the Lipschitz constant, or at least the upper bound of the Lipschitz constant. So what does this tell us? It gives a boundary of how fast the output of this function can change. And using this, using this in the existing samples, we can, for every point in the state space, get an indication of what is the highest possible value the function could actually be there, and what is the lowest possible value the function could be. And also for every point, we get some ball around it where we know so we have like this sample here, and we know that all the samples or potential samples in this ball are also positive samples. Or for this negative sample, we know that everything here will also be always negative. And so we don't really have to sample these values again, but because we already know, are these good or are these bad? So now that we have our very first model, or we just started with some random samples, and we have to get good candidates, we have to explore a little bit and add more data points to it. So we use 3 different heuristics to do this. The first one is really simple, where we just randomly sample on a grid to get just some completely unguided samples, so we're not getting stuck with some kind of heuristic. The second one is going to use the Lipschitz information, and the third one is actually a combination of what we already know from our interpolation model and the Lipschitz assumptions. Explain the second two here with some examples. So these plots are now moving into a one-dimensional space, which is not actually what our functions look like, because they were at least two-dimensional, but they are much nicer to actually show that. So we have now 2 samples, and here are also shown what are highest and lowest points that are possible according to this known Lipschitz constant. So the one orange uncertainty estimation would just say, if a point has a very high gap between the highest and lowest possible values according to the Lipschitz assumption, then the model is not probably not yet very precise there, and there is a good chance the value might be wrong. And the other green one, which already takes into account the information we have from our current model, tries not to estimate just how large is the gap, but in some heuristic way, how likely it is that a positive point will be classified as negative, or that the negative point is classified as a positive point. And for that, we're using the, on one hand, the sign of the point we want to estimate, and then we look, since this is a positive point, how negative could the function actually be at this point? And in this case, the lower bound is already a positive point, so for this point, we know that it is positive. But if you look at slightly shifted points, then we have here again a positive point, but we have a relatively large possible negative value. So if this is a point in our current model, then without any formal guarantees, but heuristically we can say this point is more likely to be mispredicted than this point or this point, where the potential negativeness of a positive point is smaller than before. And the heuristic would then just take the current interpolation model and use some optimization method to pick points that are very uncertain according to our heuristics. And on this blue picture, you would see a heat map which shows you how, for this given model, how uncertain certain regions are. And you see here the highest uncertainty is actually here at the border, where we have these very thin triangles. So these are kind of bad, and we should break them up. And also here, if you look at this part, which passes through from one negative region to another one, but passes through something that is actually positive. And we see also here, oh, this actually has also a higher uncertainty than the surrounding points. So this predictor actually is somewhat good enough or for guiding it to say, oh, maybe we should sample more here because there might be a path hidden that we cannot actually find at the moment. So now that we have our first or a model after a few iterations, we should find our candidates. And for that, we're restricting our search here to edges of our triangulation. So we'll first remove all the edges that pass through negative points, because they cannot be part of a function that is everywhere positive. And then, since we're looking for a function, we will also turn it into a directed graph. So we don't want to loop back and assign multiple control values to the same input. And then we use a simple graph search to find the shortest path, or the path with the largest minimum value through this reduced graph. And we have the paper also describes a way how to make this complete by adding additional points. But in practice, actually, just searching along the edges turns out to be good enough and easier to handle. Now that we have this candidate, we want to check, is it actually correct? And for this, we can also turn back to our sampling or exploration heuristics and just pick the most uncertain points on our current candidate. So the candidate is always positive, so we use this heuristic on how negative might it be, then we would sample first those points that might be very negative. And this leads to relatively fast classification of candidates that are spurious. And then we can use these additional points to improve our model, and ultimately we end up with an improved model and the candidate that passes through the model and is also positive everywhere. And what you see here is like the last model before doing all the final verification samples. So there are a few more samples along those edges that are then good enough that with these Lipschitz assumptions, we have a complete guarantee that this is actually a correct control function for this problem. So what kind of formal guarantees do we get from this approach? So the first one is that we're sound. So if we find a solution and our model has a Lipschitz bound that is not larger than whatever we assumed, then we will find a solution that is correct. We also have a guarantee that we are going to find a solution if one exists, with a small caveat that says that there should be a solution that is at least greater than some limit E or epsilon. So if the only solution that exists is one that passes exactly through 0, then we cannot find this with just doing finitely many samples. So you have to pick at least a tiny epsilon. And if a solution exists that stays that far away from the true-false boundary, then we will find a solution. And also, if there is no solution at all, then after doing a lot of samples, which is actually what we wanted to avoid, but I think it's still nice to have this guarantee that if you would be able to run a lot of samples, then we can also confirm that none exists. And for the case in between, we might get either answer. Okay, then let's see how well all this works. So we tried this on both some randomly generated instances and some cyber-physical system examples. Among them is one industrial case study for some voltage and current regulation. And we're going to compare our methods with two different baselines. One is a depth-first search that just uses the Lipschitz information to move as far forward as possible. And the other one is a template-based optimization method, where it tries to find parameters for a piecewise linear function. So let's first look at the random examples. For this, we use this Perlin noise generator, which is from the computer graphics domain originally, which can give us nice random problem instances. And I plotted and showed you 4 of those here. So again, we want to find this path from left to right by doing just a few samples on this function. And as you can see, our method almost never needs more than 100 samples to construct the model and find the correct function. But both the depth-first search as the optimization method are not able to find solutions for about half the instances with a limit of 2,500 samples. If we make this whole thing higher dimensional, then the depth-first search method gets a bit better, but our triangulation method is still by far the best performing method on these instances. Yeah, we have some more artificial CPS problems, and this voltage regulator. So this is our industrial case study. So you have this gray box here, which is what our algorithm assumes as the black box, but I also show you a few components, what is actually in there. So we have this analog band gap and the trimmer components. These are given as transistor level simulations in a SPICE simulator. So running a single simulation on that thing takes minutes for this example. So you don't want to run 40,000 simulations that each take 2 minutes. And what is the goal of this thing? It should provide very stable current and voltage outputs for all kinds of different conditions. And this whole setup is very temperature sensitive, both the analog part and this trimming component, which is then used to adjust the current voltage outputs from the analog band gap. And the specification component, which is also part of the black box, but for which we actually know the implementation, this is just comparing the current and voltage to the reference and giving us robustness, the worst deviation of either current or voltage. So how well are we doing on these examples? For the upper ones, which I briefly skipped, so let's just look at this band gap ones. Depending on which model we use, so we had 5 different models with different transistor speeds or configurations of this thing, and it took us, in the worst case, about 300 samples to build our model. In most cases, it were about 150 samples that we needed. And both of the other 2 methods failed to find any solution within 1,000 samples. Okay, so to conclude this presentation, I showed you a black box synthesis method that can be used to build controllers or feed-forward controllers for black box systems by using a very small number of samples, but still giving a verifiably correct solution for this problem. Thank you.
Thanks for questions. So I guess, yeah, it should. Hello? He can hear you. So I guess you see this question coming. How do you learn the Lipschitz constant, right? And so I mean, I think that there may be ways of systematically learning the Lipschitz constant if you have some access to individual modules. But you could also learn the Lipschitz constant in the data-driven way as well, right? So what are your thoughts?
Yes. Because I actually had a slide in there, but I skipped it because of time. So we have a way, or we proposed a way how to dynamically find those Lipschitz constants. So there are methods to take data samples, and you can get an estimate of what the Lipschitz constant is probably going to be. The best ones are statistical methods, which are a bit problematic in our setup because we cannot guarantee any IID distribution or anything about our samples. Because actually quite the opposite, our samples are very focused on the parts where we already found candidates. So they are we have a lot of samples where we explored for candidates, and in the local search space around samples, around potential candidates, but we don't have like uniformly distributed samples or anything. So we use a simpler estimator, which is called the Strongian estimator, which just looks at what is the maximum difference between any 2 existing samples and then adds a safety margin to that. And you can use this while computing the model and then just update all the Lipschitz parts with the updated Lipschitz constant. And maybe also another thing, all this guiding of the sampling still works if you have a wrong Lipschitz constant. It's just that the final verdict is wrong. So having a different Lipschitz constant doesn't really shift what is the best point according to any of the heuristics. But the stopping criteria of I have found a solution that is correct might be wrong.
Any other questions from the audience? Maybe I have a question, more of a clarification. So your path is good to visualize for one input. What would you do if there are multiple inputs? It's no longer a path, right? It's more of a surface that's going from one end to another.
Yes. So the current method is actually focused on this with one input, but we might have many different outputs. So in this case, it really is a path. But as some future work, we already tried methods where we are actually trying to find these surfaces of multiple multiple inputs as well. Where, as you said, then it's more like a cut through this space in the surface. But this is future work and wasn't part of this paper.
So the other thing, I looking at your problem, you could pose it as finding a path where you give the guarantee for the largest possible Lipschitz constant. So in other words, you could find a path that still works even if I increase the Lipschitz constant assumption, right? So you can get the most robust path in this problem. Have you thought about that?
Yes, this is actually what we are to some extent doing, because here we're searching for the candidate that has this largest minimum value, which roughly corresponds also to the path which is the most robust to changing Lipschitz constants.
Very good. Very good. All right, so any further questions?
I mean, I have more of a clarification. So I don't think this is working, but okay. So my question was like, is there any state in this function f, or is it time dependent?
No. So we're assuming a stateless function.
So I guess the follow-up would be,
but
if there is state, then it would, I guess, complicate.
Then yes.
Thank you so much. So we have the break right now. We'll be back at 11. So let's thank the speaker one more time.